All right, so now let's talk about the preparation of alcohols, how we make alcohols. This is going to involve a lot of stuff that we've already seen, as well as some new techniques, right? So we know how to make alcohols from alkyl halides via substitution. So if we have a primary, and this would be in the presence of a strong base, strong nucleophile like the hydroxide ion, this will proceed through an SN2 mechanism and give us our alcohol. You can also do the same thing with a secondary, but then the major product is the elimination. So the minor product would be an alcohol. And then if it's a tertiary alcohol, you can do the same thing, but you would use the weak nucleophile, weak base of water, and that would proceed through an SN1 mechanism to give you a tertiary alcohol. Okay, so if you had a secondary, maybe what would be even more efficient would be to first do an elimination, and then we of course know how to convert our alkenes into alcohols as well, right? So using dilute sulfuric acid, we can make an alcohol, and this would be the Markovnikov product. It would go on the more highly substituted carbon. We could do the same thing using this mercury catalyzed reaction. It's also going to give us the more highly substituted, or the Markovnikov product. Remember, the oxymercuration is good because there are no rearrangements that will occur, right? So you don't have to worry about any carbocation stuff. And then if we wanted to form an alcohol on the less highly substituted carbon, so the anti-Markovnikov alcohol formation, we can use the BH3 and THF followed by hydrogen peroxide and sodium hydroxide. So that would give us the anti-Markovnikov addition, those hydroboronation reactions, right? So these are reviews from chapters 7 and 7? Yeah, 7 and 8. This says 9. That's actually not right. So this would be 8. Right? Yeah. Okay, and then in terms of forming our diol, so remember we learned how to name these, but we also know how to form these using two different methods, either the anti-dihydroxylation, which would be using those peroxy acids. This is the peroxy acid, and then followed by acid, H3O, or we could use the osmium oxide, or another way to do this was with the potassium permanganate, right? And that would be a syn dihydroxylation. So another method that we're going to learn about in terms of creating alcohols is by doing so through reduction of a carbonyl group. Okay, and this is one that we're going to spend a good bit of time on here. So what do I mean by reduction of a carbonyl group? So remember, we can calculate the oxidation state of carbon. This is something that we learned kind of in general chemistry. I'm not going to focus on how you calculate oxidation states, but basically it's a measure of how many carbon oxygen bonds there are in a given molecule. At least that's what we're going to consider it to be here in this chapter. So in terms of oxidation states, right, if you had a carbon that was bound to 4 hydrogens, that would be the lowest oxidation state, all the way to a carbon that's bound to 4 oxygens or has 2 carbon-carbon double bonds, and that would be the highest oxidation state that carbon can have, right? So going this way would be oxidation, and then going this way, we would call that reduction. So we can form alcohols by reducing carbonyl groups, right? So I guess actually this is a specific case with methanol and formaldehyde, but really it's the reduction of this carbonyl group would give us an alcohol. So we're going to learn a few techniques to do that. Okay, so again, this is what we're doing. This is, again, this particular section is preparation of alcohols. It's all about starting with an carbonyl group and then reducing it to an alcohol. All right, there's three ways that we're going to learn how to do this. One of these is actually already fairly familiar to us, and that is catalytic hydrogenation. So that's using hydrogen gas in the presence of either platinum, palladium, or nickel. So just like we use this technique to reduce a double bond, we can also use it to reduce a carbonyl group to an alcohol group. All right, and although this is possible, it turns out to be a fairly unpopular method of doing so. You need some fancy equipment because these reactions take place at really high temperatures and pressures. Plus these catalysts, these palladium, platinum, nickel catalysts, they're not necessarily cheap, right? So this is actually kind of one of the least popular methods for doing so, but we could do it this way. Way more common is using these two reducing agents. This is sodium borohydride, and the key word here is hydride. And we'll get to why that is in a second. The other one that we're going to see is lithium aluminum hydride. Okay, so another hydride. And these are methods that we can use, these two reagents we can use to reduce a carbonyl group to an alcohol group. So let's focus on sodium borohydride here for a second. Sodium borohydride you would use in the presence of some protic solvent. All right, so you have to use it in the presence of an alcohol or water. We'll see why that protic solvent is really important here in a second when we look at the mechanism. But again, the main feature is that you're going to convert your carbonyl group to an alcohol group. Okay. So how does this work mechanistically? So when you hear the borohydride or aluminum hydride, this hydride implies a hydrogen that has two pairs or a pair of electrons and thus a negative charge, making it a nucleophile. All right, that's the big key of these hydrides, is they have nucleophilic hydrogens, which is kind of weird. We're not used to seeing hydrogen playing the role of a nucleophile. But so what happens in these reactions is, and I guess actually first let's take a step back and talk about carbonyl groups real quick. One feature of a carbonyl group is you have this very polar bond right here where there's a partial negative charge on the oxygen and thus there's a partial positive charge on that carbonyl carbon. So carbonyl carbons like to play the roles of electrophiles. They accept electrons really readily. And so that's what's going to happen in this reaction mechanism here. We're going to have this nucleophilic hydrogen that's going to attack that electrophilic carbonyl carbon. And then what has to happen here? Well, this carbonyl carbon can't have more than 4 bonds. So at the same time, it's going to bump that pair of electrons up to that oxygen. So this would be a nucleophilic attack of that nucleophilic hydrogen. And so that's our first step there. Now this pair of electrons would love to come back down. But again, it can't do that because that means that that carbon would have more than 4 bonds. Maybe it could if it could kick off one of these groups here, but if it's a ketone or an aldehyde, basically if this R is a carbon or a hydrogen, they're not good leaving groups. They're in fact super terrible leaving groups. So it's kind of stuck here. And so that's when this next step, the protonation step is really important. That's why you need a protic solvent, is because the last step is that alkoxide ion is going to reach over and grab a proton from that solvent, whether it's an alcohol or water. And so that's how you get your reduction of your carbonyl group using these hydrides. So now let's talk about the stereochemistry of these reductions. Good news, super easy. Remember that sp2 hybridized carbons will lie in a plane, right? So this is all these atoms here are lying in the same plane. They're flat, so that means that this nucleophile can attack readily from both sides, no problem. Right, so that means that when we get these, we're going to get a mixture, a racemic mixture of both possible stereoisomers. There's no stereospecificity to these reactions. we will always get a racemic mixture. So the other one that I sort of introduced before, but this is lithium aluminum hydride. Again, what do you think when you hear hydride? You think nucleophilic hydrogen. And so it does the same thing. It can reduce carbonyl compounds down to alcohols. Notice that they're really, really, really similar in terms of structure. Again, the whole shtick is you have these nucleophilic hydrogens, but a lithium aluminum hydride is actually more reactive than sodium borohydride. So you can't have it, actually, if we just go back, notice here that you can't have lithium aluminum hydride in the presence of alcohol or water. You have to do these in two separate steps. So first you treat your carbonyl group with lithium aluminum hydride, and then you add some sort of protic solvent to it in order to protonate that group. This textbook, I have no idea why, but it likes to abbreviate lithium aluminum hydride, LAH. I have no idea why that's so much easier than just writing that. That's what I've always seen it as. So you're going to see me write it like this. But again, the textbook likes to use this abbreviation LAH. So just keep in mind that's lithium aluminum hydride. All right, and then mechanistically, literally identical, because again, the whole shtick is that these hydrides, they have nucleophilic hydrogens. So the first step is that nucleophilic hydrogen attacks that electrophilic carbonyl carbon, and that's going to bump that pair of electrons up to that oxygen. And again, it's just sort of stuck here at this alkoxide ion. This pair of electrons would love to come back down, but there's no good leaving group to do it. So instead, it's just going to sit there until you treat it with your protic solvent, at which case it will reach over and grab a proton from that protic solvent, thus becoming the alcohol group. Okay, but so notice that we have, again, nucleophilic attack, but our nucleophile is that hydrogen. Okay. So then there are some slight differences in these two methods that we've seen, as at least in terms of ketones and aldehydes. Lithium aluminum hydride and sodium borohydride are the same. They will reduce that carbonyl group to an alcohol. They will not, however, be able to reduce an alkene. They can't reduce double bonds, right? So this is in contrast to if we did use hydrogen gas over platinum or palladium, we would get reduction not only of that carbonyl group, but also of the alkene as well, right? So these differ in terms of what's happening with these carbons here. Are reducing agents or hydride reducing agents, they'll preserve a carbon-carbon double bond, whereas that hydrogen gas over palladium, nickel, platinum, those won't. It'll reduce both the carbonyl group as well as the alkene group. All right, so let's do a little bit of a summary. So again, this would have been chapter 7 stuff, where we learned about alkyl halides and how we can use substitution reactions to create alcohols. These are things that you should, in terms of mechanism, you should definitely know the mechanisms of SN2 and SN1 substitutions. Okay. In terms of well, no, the first one was actually regioselectivity. You're always going to, it's just going to be a substitution, so there's not sort of any regioselectivity concerns. And then in terms of stereoselectivity, we have to be very concerned about that with the SN2 reactions, right? These have these inversions in stereochemistry. Whereas with tertiary alkyl halides, SN1 reactions are non-stereospecific. Okay. When we go to our alkenes, now we had, so this was chapter 7, I had said. Alkenes we learned about in chapter 8. We had 3 different methods to prepare those. In terms of the dilute sulfuric acid, again, you should know the mechanism for that. Okay, these are these acid catalyzed hydration reactions. In terms of regioselectivity, in terms of regioselectivity, yes, these are the Markovnikov. And then the third method that we had, those hydroboronation reactions, those were the anti-Markovnikov. And then in terms of stereoselectivity, there's no stereoselectivity in the presence these acid catalyzed hydration reactions. Remember, these go through the carbocation intermediates. When it comes to the mercury catalyzed, these were anti-additions. And when it comes to the hydroboronation reactions, these were syn additions. These really only come into play when you've generated two new stereo centers in your molecules. So for something like this, it really wouldn't matter. But if you had something like this, then all of a sudden the syn and the anti-addition are really important to keep in mind. All right, and then the last ones that we had learned about, these are our new ones. So these are just from chapter 12. These are our reduction methods. In terms of mechanism, you don't have to know it for the our catalytic hydrogenation, but you should absolutely be able to do it for our hydrides, right? That's that nucleophilic hydrogen being involved in those reactions. Good news in terms of regioselectivity, there's not anything that you have to consider there, as well as stereoselectivity. There's no stereoselectivity. You'll always get that racemic mixture if a stereocenter is formed.